with number 27. Okay. Finding the inverse of a function. Now, it doesn't matter what type of function it is. The first step is the same in terms of finding the inverse. Since f of x is y and y are pretty much synonymous, we're going to switch the location of x and y. So instead of y equals x minus 2 cubed minus 8, it's going to be x equals y minus 2 cubed minus 8. And now our next step is to isolate y. So we've got to do whatever it takes to get the y by itself. So I'll add 8 to both sides, x plus 8, y minus 2 cubed. To undo the cubed, I have to take the cube root of both sides. The cube root of x plus 8. That's all under the radical. So this side, suddenly, since I'm taking the cube root of a cube, becomes y minus 2. And this side, cube root of x plus 8. And then I'm just going to add 2 to both sides to finish. Now, this 8 and 2 are not like terms, so don't combine them. This just means that our inverse function, which I write f inverse of x, is the cube root of x plus 8 plus 2. The 2 is outside the radical. Okay. Switching from radicals to rational exponents. So anytime you have a radical, a cube root, square root, sixth root in this case, we can write it using a rational exponent, which means a fraction exponent. So I can take this whole thing, 64, a to the 14th, b to the 12th, and raise that to the 1/6 power. Sixth root and 1/6 power are the same thing. So that becomes 64 to the 1/6 power, a to the 14/6 power, because I'm just multiplying, right? This has an exponent of 1. I'm just multiplying. When you raise a power to a power, you multiply. B to the 12/6 power, and then it's just a matter of simplifying each of those pieces. So 64 to the 1/6 power, I'm going to assume is 2. I'm going to check that. 2, 4, 8, 16, 30. Yes, it's 2. 14/6 is 7/3, so I'm just going to simplify a fraction, and 12/6 is 2. So that's writing it using rational exponents. These are equivalent. Okay, the next one asks us to write it using a radical. So it's like I'm going in reverse here. So that says the 5th root of x to the 16th times the 5th root of y squared. And you can, because these are both 5th roots, we can kind of multiply and put them together. And then it says we should also simplify. So imagine you've got 16 x's underneath this radical, and we're circling groups of 5. That means that we're going to bring 3 x's out. 5th root. There will be 1 left inside, and y squared. So this is my simplified form. Okay. Graph radicals using the transformation rules. So it helps to know what the parent function looks like. The parent function is the square root of x. And so I could take a black pen maybe and draw out what the square root of x looks like. This is the parent function. Has point here, square root of 1 is 1, square root of 4 is 2, square root of 8 is, or square root of 9 is 3. So the graph looks like that. And then we're going to transform that graph by going left 1 and up 4. So this point here is going to go left 1 and up 4. Left 1, up 4. Left 1, up 4, like that. Left 1, up 1, 2, 3, 4. It's making my eyes hurt. So small. Okay. There's my transformed graph, the green one. Oh, parent function, square root of x. Okay, the transformations, I just wrote, I didn't read the question before starting my work. Left 1, up 4. Okay, to do the domain and range, it's always a good idea to label the ends of the graph. So this one is going up towards infinity, infinity, right? When x is infinity, y will be infinity. And this endpoint here is negative 1, 4. So when I do the domain, I'm going from left to right, so negative 1 to infinity. I'm going to include the negative 1 because there's an actual point here. And when I do the range, I'm going from the bottom to the top, so 4 to infinity, looking at the y values. Okay, next page, where are we? 33. Okay, solve equations with radicals. So we have an equation here with a cube root. The first step, here's my highlighters. Again, one of our themes is isolating. So I'm going to get that part of the equation by itself by first subtracting 9 from both sides. So this becomes 4. Cube root of 3x minus 1. And then I'll divide by 2, because this says 2 times the cube root. So divide by 2, and we get 2 equals the cube root of 3x minus 1. Now this might have already come up just a moment ago when you're trying to undo a cube root. I think we were trying to undo a cube. Yeah. But to undo a cube root, you cube both sides. So I'm going to cube this side and cube this side. This becomes 8. This simplifies to 3x minus 1. Add 1. 9 equals 3x, so x equals 3. And it's always a great idea to plug your solution in just to make sure that it works. Test it out. So if I put a 3 here, this is 9 minus 1, that's 8. Cube root of 8 is 2. 2 times 2 is 4, plus 9 is 13. You could write that out too, but I like to check my work a little bit. Okay, solving more equations with radicals. Now this one is a little bit funky because we have variables on both sides. So the radical here is already isolated. It's the only part of the equation on the left side here, or the right side. So I'm just going to start by squaring both sides to undo that radical. So this side, this one's easy. That just becomes 13 minus 2n. This side, right, I have to do n minus 5 squared, which is not n squared minus 25 or n squared plus 25. You gotta FOIL it. It's been a while since we encountered one of these, and I had to get really ornery with people. It's n squared minus 10n plus 25. Okay, now I'm faced with a quadratic equation. This is like my best case scenario. I love these. I love solving quadratics by factoring. So let's be hopeful that this is factorable. So I get n squared minus 8n plus 12 equals 0. Ooh, yes, it's factorable. N minus 6, n minus 2. So my solutions would be 6 and 2 with my mini equations. Now, this is one where it's definitely good to check, because when we plug these into the original equation, like before we squared it, if you go plug the 6 in up here, you've got 13 minus 12. Oh, that might work. Okay, let's try. Let's check. I don't have a lot of space. Let's get a Post-it to check. Where are you? Definitely want to check these though. Okay, so we're going to check 6 by plugging in 6 minus 5, and I got to plug it into the original equation, not the one with that's squared, the original one, equals the square root of 13 minus 2 times 6. Okay, so this is 1 equals the square root of 13 minus 12. 1 equals the square root of 1. Okay, yes. So now we'll check 2. 2 minus 5 equals the square root of 13 minus 4. Negative 3 equals the square root of 9. No, it doesn't. So that's extraneous. So our only solution for this one, the solution that worked, was 6. So 2 is extraneous. Okay. Multiply and simplify radicals. So when you multiply radicals, right, you multiply coefficient times coefficient. So I'm going to put a coefficient there so we can see it. And radicand times radicand. So I've got 4 square root of 48, x to the 4th, y to the 9th. Now, if you like to go with the visual route, you're going to make a factor tree for 48 which is 8 times 6, 2, 3. I'm going to simplify that, so that becomes 2, 2, 2, 2, 3. You've got 4 x's, and you've got 9 y's. 4, 5, 6, 7, 8. Now, you know what? I'm really doing it this way because this is what I've been doing with my Algebra 1 classes all year. So, you know, if you can come up with a little shortcut for taking the square root of x to the 4th, absolutely, please do it. I'm actually not sure why I'm doing it like this, but it's nice to circle the pairs because you can always go back to your roots with this, you know? Go back to the roots. Here we go. How many y's are we going to bring out? How many x's? So I'm going to bring out a 2 and another 2. I'm going to bring out 2 x's and 1, 2, 3, 4 y's. And what's left under the radical is 3y. So this becomes 16 x squared y to the 4th square root 3y. Okay. Multiply or divide rational expressions. Okay, these are fun. Keep, change, flip is how we divide, right? This is just a fraction. 12 minus x. Let's factor this while we go. X plus 6, x minus 6. Flip this over and factor this. Okay, 3x, x, plus 6 maybe? Yep, minus 1. So this becomes 18x minus 1x, and that's 17x. That looks great. Now I can start crossing stuff out. That's the fun part. Cancel that, cancel that. Yes, you can cancel 12 minus x and x minus 12. They're not equivalent, but they will simplify to negative 1. So this becomes negative 1 times 3x minus 1 over x minus 6. Or if you want to distribute the negative 1, it's negative 3x plus 1 over x minus 6. Either one of those answers would be appropriate. Okay. Adding and subtracting rational expressions. Just like adding and subtracting fractions, you cannot add these as written because or subtract them because the denominators are different. The denominators have to be the same. And one of the things that's often helpful is to put those in parentheses so you can see like, hey, these are two totally different factors. So in order to make them the same, I'm going to multiply this one by x minus 4 and this one by x plus 7. Distribute, so I get 5x squared plus 35x over x plus 7, x minus 4, 2x minus 8 over x plus 7, x minus 4. Now the denominators are the same. Now we can subtract, put them together. Subtraction is a little bit harder because when you go to combine those like terms, it's 35x minus 2x, so that's 33x. But it's also minus negative 8. We have to like distribute that, minus negative 8. We're subtracting this whole expression here, so that becomes plus 8. That's good. Okay. Page number 42. I think I'm going up to 43. I'm going to go up to 48. I'm going to finish this unit. Well, I'll go to 47, I think. Okay. Solving rational equations. Now, this is a lovely rational equation because it's about the quickest one that we did. Since it's just of the form fraction equals fraction, I can solve this one by cross multiplying, the one thing that everyone loves to do even when it's not appropriate. So I'll do 3x times x plus 3 equals 2 times x plus 5. It does become an equation, right? You got to have that equal sign in there when you cross multiply. 3x squared plus 9x equals 2x plus 10. Oh my goodness, my favorite thing. It's a quadratic equation. I want to solve by factoring. Combining only the like terms here, and then factoring. So let's see, 3x and x. negative 10. So I need one negative and one positive. Gosh, it's not 5 and 2. That's not working. Because that must be 10 and 1. Let's see. Yeah, it's 10 and 1. Okay, plus 10 here, minus 1 here. So that's 10x minus 3x. That's how I got to the 7x. Okay, so make your little mini equations. 3x plus 10 equals 0. So x equals negative 10 thirds. X minus 1 equals 0. X equals 1. I do want to check to make sure that these are not excluded values. So I just want to take a quick look and make sure, okay, you know, negative 5 would be an excluded value and negative 3 would be an excluded value. So if I came up with those as solutions, I would know they are extraneous. But these are, neither one of these is an excluded value. So I feel pretty good about those being the two solutions. Of course, you can always check them by plugging in. So this would be 3 over 6 equals 2 over 4. Yes, it does. Okay, so you can check them by plugging them in. All right, the next one amps up the level of difficulty just a little bit, because to solve this equation, right, we want to have all the denominators the same, right? We can't just cross multiply. So if we can get all the denominators the same, then we can set the numerators equal to each other. So when I'm looking at what I have, 6x and 6, I'm going to change the common denominator to be 6x. That's what I want all the denominators to be. So it's like this one needs an x, this one needs a 6, so multiply by 6 over 6, and this one needs x. So I'll do x squared minus 2x over 6x minus 6x minus 12 over 6x equals negative 1x over 6x. So I've got to make sure I got these guys in parentheses here. Okay, now once I have all the denominators the same, I can essentially ignore the denominators and I can just set the numerators equal to each other. Do have to be a little bit careful here because of this minus sign again. So it's x squared minus 8x plus 12 equals negative 1x. Uh-oh, what have I done wrong? Have I done something wrong? Maybe not. Let's keep going. I'm suddenly concerned. Oh, no, I'm cool. I'm cool. Okay. It's a quadratic, setting it equal to 0 so I can factor. So x is 3 and 4. And again, I'm going to check and make sure those aren't extraneous. That seems fine. Right, the only excluded value would be 0, so these are okay. All right, asymptotes of rational functions. This is where I need to have my asymptote rules ready. When I'm trying to find the horizontal asymptotes, right, I'm looking to see what the degrees are. So the degree of the numerator and denominator is the same, it's 1. So that means my asymptote is 1/2. And it's y equals 1/2 because I got to write this down for myself. Hoi vux. If I want a horizontal line, it's got to be y equals. My vertical asymptote is x equals something. And to find the vertical asymptote, I'm trying to find the excluded value, like what number will make the denominator 0. So I just need to solve a little mini equation to figure that out. And it's negative 3/2. That's my vertical asymptote, negative 3/2. That's just my work. When we're thinking about these rational functions, we kind of know the basic shape of a rational function. The end behavior, the graph is always going to be approaching the horizontal asymptote. So if the horizontal asymptote is at 1/2, that's what the ends of the graph are approaching. They get closer and closer and closer to that horizontal asymptote. To find the zeros of any function, you replace f of x with 0 and then you solve. So I'll do that on a little piece of scratch paper here. Set f of x equal to 0. 0 is the same as 0 over 1. And then if I want to solve this, I can cross multiply. So 0 times 2x plus 3 is 0 equals x plus 1. So x is negative 1. That's my x-intercept, or my 0 of the function. You could write it like this, or you could write an ordered pair, negative 1, 0. Okay. Looking at the next one, again, for a horizontal asymptote, you have to look at the degree. The degree of the numerator is less than the degree of the denominator, so it's just automatic, y equals 0. To find the vertical asymptotes, we need the excluded values. What are the numbers that will make the denominator 0? One of them is 5, because that would turn that into a 0, and the other is negative 2. The end behavior, the graph always approaches the asymptotes. The horizontal asymptote, sorry. And what are the zeros of the function? Well, again, I would have to set up a little equation. This one might seem silly. 0 equals 7 over x squared minus 3x minus 10. Let's make that a little more visible. Cross multiply, so you get 0 equals 7. Well, that makes absolutely no sense, right? We can't solve that equation. It doesn't have a solution. And since I can't find a solution to this equation, that means it doesn't have any x-intercepts. There are plenty of graphs that never touch the x-axis. This is one of them. No zeros. Okay, we'll stop there because the next section is about exponential and log, which was the next unit.